Hey guys, hello everyone and welcome to the channel. Now in this particular video, we have started a particular new kind of things where I'll be explaining you about quantum mechanics, and it's not just going to be a kind of series in which we'll just learn quantum mechanics, right? We'll also try to understand the things. So that's why I have decided that I should go from the very basic, and the first topic I have already made, that is what is wave function, and I guess most of you have watched that video. If you have not watched that video, I'll just link that in the I button over here. So you can click on the I button and you can watch that particular video, that what actually wave function is, what is the physical significance of that, why do we find out a wave function, what is the probability density and all. Okay, so these are few things which are actually needed to be understood in order to initiate your study about quantum mechanics, right? So today's video is about the acceptable wave function. Now in quantum mechanics, it's not like that all the types of wave functions will be accepted. Okay, there are many types of wave functions. Wave function means a function which represents a wave, right? And I already explained that wave is nothing but a motion in the to and fro direction. So any to and fro kind of motion cannot be an acceptable wave function in the quantum mechanics. So there are certain limitations, there are certain points regarding that. So we'll try to understand those points. First of all, we'll try to know those points, and then we'll try to understand that why actually those restrictions or why those properties are required by a particular wave function. All right. So in this particular way, we'll try to understand, and we'll try to also solve some questions at the end of this particular video. So there are 4 or 5 basic properties which are required by a particular wave function in order to become an acceptable wave function. Okay. The first property is that the function must be single valued. The function has to be single valued wave function. The second is that it has to be a finite valued wave function. That means it should have a finite value, or you can also say, in some other words, you can also say that it has to be normalized wave function. I'll talk about these things. Okay. Then the third thing is that it must be continuous in over a given interval. So for a given interval where you are actually trying to find out your wave function, it has to be continuous. That interval can be of time or it can be of space. That means of the direction. Okay. So it has to be continuous. So 3 points till now. First, it must be single valued. Second, it must be finite valued, or it should have a finite value, or it must be normalized. And the third is that it must be continuous. The fourth important thing is about the first derivative of the wave function. So if you have a wave function, if you take the first derivative of that, you take del by del x of that particular wave function. So that value, that particular first derivative of your wave function has to be also continuous. Okay, so that first derivative of a wave function also has to be continuous. That is the fourth point. And the last and the most important point is that it should follow the boundary conditions. What are boundary conditions and all? We'll try to understand them. Okay, so now let's look upon all these points one by one. So the first thing is that the function has to be single valued. So what does this single value means now? Okay, all right, so let's consider 2 wave functions over here. Let's draw them in such a way. The first wave function is like, let's say the first wave function goes something like this. Okay, and the second wave function goes something like this. Okay, so this is, let's say, my psi1 and this is my psi2. Now what does this single valued means? Single valued means that if you draw a parallel line along the y-axis, or if you draw a perpendicular line on the x-axis, it should give you just 1 point on the wave function. So that means if I draw a perpendicular line at any point, okay, at any point if I draw a perpendicular line on the x-axis, so I should always get a single value on the wave function, which is there in my psi1. So psi1 is this will be called as a single valued wave function. Okay, now what about the second one, the psi2 over here? Now in psi2 you will see that if I draw a perpendicular line on the x-axis, so I'll be having multiple values of multiple points on the wave function over here. Even if I extend this point, so I'll be getting like 1, 2, 3, 4, 5. So it's not a single valued wave function, it's a multi-valued wave function. So this is multi-valued wave function. Now why this point is so important, why a particular wave function has to be single valued, what is the significance of this, right? So this is theory that it has to be single value. Now we'll try to understand that why actually it is needed. So you already know this thing, that if you draw a particular wave function, and if you just square that up, that means if you take the complex conjugate product of the complex conjugate of that, and if we are doing it in a one dimension, so if we multiply with dx over the range of the interval, so you should get 1, right? This is what we call it as probability density. So it gives you probability of finding particle. Okay, so basically if you are doing it at a certain point or at a certain like value of x, so this particular wave function is going to give you about the probability of finding particle at that particular point. Now that means what? That means over here in this wave function, the first wave function, if I want to find out the probability of finding my particle, so I just have to square this up. So the square of this will again be the positive side itself. Okay, it will be just on the positive side. So this red colored lines are now showing me the probability density graph or probability density curve. So if I have to find out the probability of finding particle at, let's say, x is equals to certain value a, so this particular value of the wave function is going to give me the probability of finding particle. So there is just single probability of finding particle at a single value of x. So at every value of x corresponding to all the values of different values of x, you will have different probabilities of finding particle. It may be high, it may be low, it depends upon the wave function, but for every corresponding value of x, you will have a definite probability of finding the particle. Now let's try to figure it out the same thing in the psi 2. Will it happen or not? So over here if you see, so the definition is same. That means at a particular point on x, if I draw a perpendicular line, so these has to be, so the probability function first of all for this, since it's a positive wave function over here, so the probability will also be the positive values only. Okay, the probability will also remain the positive itself, like that. Okay, so that means if I draw a perpendicular on the x-axis, and let's say this is x is equals to some value b, and I want to find out the probability of finding particle at x is equals to b. So what I have to do, I just have to see that how many probabilities I will be having in the probability density curve. So here you can see I will have multiple probabilities for a particular value of x. So you cannot decide that what is the actual probability of finding particle at that certain value of x. So that means what? This is something which is not acceptable in quantum mechanics. There should be a definite probability of finding particle at a certain value of x. Okay, so if you are fixing the value of x, you should get a certain probability. You should not get multiple probabilities, otherwise this doesn't make sense, right? It means that it has probability this much also, it has this much probability also, it has this much probability also of existing at this particular value of x. So that is not something which is acceptable, right? So that's why this first point is about actually the probabilities of finding particle at a certain value of x. So that's why it has to be single valued, so that you just get a single probability of finding particle at that corresponding value of x. All right, so that was the first point. Talking about the second point, which says that the function has to be finite valued or it has to be normalized. So the second point is actually very simple to understand. Now once we have gone to understood that, fine, we have a wave function which has to be single valued. So let's consider a single valued wave function. And now in this case, what it says that it has to be a finite valued wave function. That means it has to be normalized. What does that mean? It means that if the particle is there in that system, and if you are restricting the system, let's say from here to here, these are the boundary conditions, let's say x is equals to 0 and this is some value of L. So if my wave function is there in this particular range, so that means what? That if it is a normalized wave function, then only you will get this thing, that is psi star psi dx from x is equals to 0 to L. This is going to give you 1. That means the probability, the total probability of finding out the particle within this range will be 1. So in other words, you can say that the function has to be a finite valued, or you can say that it's a normalized wave function. So both the points are actually like fulfilling each other, or they are just explaining each other. Finite valued means a particular wave function which on solving gives you a definite value, and normalized values also means, that means when you multiply it with certain complex conjugate of that wave function, you get 1. So the overall probability, the highest probability which you can get of finding anything could be 1. The lowest probability which you can get for anything to happen is 0. So there is either probability of happening nothing to a system or happening fully of a system. So 0 and 1 are the lowest and the highest probabilities which can happen. So that's how your normalized wave function is being satisfied. All right. So now the second point is also understood, that yes, why my wave function has to be finite value, because it has to fulfill the overall probability of the function to be 1. So because it has to be normalized overall, that's why it has to be a finite valued wave function. So that's the second point. Talking about the third point says that it must be continuous in the given interval. Okay, it has to be continuous. So let's try to understand that as well. All right, so here I have taken 3 examples of wave function. The first one, these are the intervals in which the function is defined. Okay, so let's say this is x is equals to 0 and this is x is equals to L, and the wave function is a function of x. Okay, this is again 0 and L, this is again 0 and L. So the condition says that the wave function has to be continuous, which you can see from the graph itself that the first one is a continuous wave function. Okay, it's a continuous wave function. The second one is a discontinuous wave function. Whereas the third one is also discontinuous. Why discontinuous? Because it is broken up over here. Now what actually it means, why it is required to be satisfied by this particular condition. So again, the same concept will come over here for the probability of finding particles. So if this is a continuous wave function, if I draw the mean position, the mean line of this particular wave function, so I can see that the probability of finding out the particle will be given by these points. Okay, this will be given by something like this. What does this mean in this particular discontinuous wave function? It means that if I want to draw the probability, so the probability will be something like this. The probability will be this, and then the probability will come like this. Okay. So that means there is a certain area or there is a certain value of x, okay, where there is no probability of finding particle. That means there is no particle in this region. So what does it actually means? It means that if you have particle in this particular region and you have particle in this particular region, now you don't have particle in this region. Okay, in this region there is no particle basically, and then you again have particle in the right side of the region and again in the last region. So that means what? That means you have a certain area or you have a certain region in the wave function where there is no particle, which is not actually correct. The particle has to be present, like the probability of the particle has to be everywhere, right? There can be certain points, actually those are called as nodes, which you can see over here. These points are called as nodes, which are actually acceptable. Why? Because these are just points. If you have a certain area or a field where the particle cannot happen, then the particle cannot tunnel through it to the other point. For tunneling, the space or the difference has to be very, very small. So these things you will understand when you will study quantum tunneling and all. Okay, that why tunneling is not possible through a broad like potential barrier or through a broad area where there is no probability of finding out the particle. Okay, so this particular area suggests that there is no particle, which does not makes any sense, right? You have particles, then you don't have particles, so it does not makes any sense. So that's why this particular this particular thing has to be discontinuous, and this does not has to be accepted in order to form a acceptable wave function. So for acceptable wave function, this property is not acceptable, right? Same goes for this particular one. You can see that over here, if this is the mean position, then actually at this particular value of x, you have two positions or you have two values. Although the wave function is discontinuous, but yet you have two values of the wave function. Or you can say that at a particular value of x, the wave function is multi-valued. So again, we are going back to the previous thing where we have seen that a wave function cannot be multi-valued. It has to be single valued. So here the wave function is actually discontinuous, but in the order of discontinuity, it's also showing us multi-valued characteristic. All right. So either the discontinuity of this kind or the discontinuity of this kind is not acceptable. You can see that here the probability jumps from here to here. Like you have some lower probability and then it jumps to certain higher probability, which is also not acceptable, right? So there are many ways to interpret this, but yet the overall like summary of this is that a continuous wave function gives you two things very importantly. First of all, you have continuous probability of finding out the particle at every value of x. Second thing is that you don't have any region in which there is zero probability of finding particle and the particle is now present on the other side. So that does not happen in a continuous wave function. whereas in the discontinuous wave function it happens so, which is against what we take or what we accept in a quantum mechanical for a quantum mechanical particle or for a quantum mechanical wave function. So that's how you can understand this particular point, right? Now moving forward for the next point, the next one says that it should have a continuous derivative on the given interval. So let's first understand that what first derivative of a function means. Okay, so for any function, let's say the function is any curve. Okay, any curve it is. So the first derivative at any point, let's say if I have to find out, this is at x is equals to a. So if I have to find out the first derivative means the tangent at that particular point. Okay, so the first derivative tells us about the tangent at that particular point. So d, if this function is fx, so d of fx by dx, this actually gives you the tangent at, if you are doing it at, let's say x is equals to a, so this gives you tangent at x is equals to a. So you are getting tangent at that particular point. Again, if you want to find out the first derivative at this x is equals to b, so here you will be having again one more tangent over here, okay, like this. So at any value of x, your first derivative is going to give you the tangent at that particular point. Now it says that the tangent has to be continuous. From the point you can say that the tangent has to be continuous or it has to be single valued. So it means that, let's say if I take a wave function like this, let's consider a wave function in this way. So if this is a type of wave function which I am considering, so what is going to happen? Will it be a acceptable wave function? So it is continuous, it is single valued also, because it is having a single valued for every x. Okay, so if this is my mean line, let's say, okay, so is this wave function an acceptable wave function? So no, it's not acceptable wave function. Why? Because if you check it out at this particular point, you will find out that you have two tangents. One tangent will go in this direction and the other tangent can also go in this direction. What you have to do, you just have to draw a tangent at that point. Again, at this particular point, again you have two tangents, one going in this direction, the other one going in this direction. So at every crest, or you can say that at every peak, you are going to get two tangents values. So which is not acceptable, right? You cannot have two tangent values for a wave function. So that's why you can say that the wave function has to be, in the mathematical term, we call it as the wave function should have first derivative to be continuous. So it should have a continuous first derivative. So now I guess you understood, right? So first derivative means the tangent for that particular wave function at that particular point, and a continuous tangent means that you should only get a single value of tangent or a single direction of tangent at a particular value of x for the wave function. Okay, so you should not get multiple values. The last point, which says that the boundary condition must be satisfied by the wave function. Now what is the boundary condition? So this you will cover up when you will study the quantum mechanical systems like the particle in a box or hydrogen atom problem. So for them you will find out that at boundary condition or at boundary, what happens, that your wave function will be 0. Okay, so at boundaries you will find out that a wave function actually is equals to 0. So if it is particle inside a box, so it will start from 0 and it will end up at 0. Okay, so this is how the wave function will be. So it will start from the 0 position, it will end up at a 0 position. Same goes for, let's say you want to draw a 3 crest one, so it will also start from 0, go for 0. So the boundary condition is that at the boundary value it has to be 0. Is the potential energy is too high, and due to those high potential values, your wave function cannot exist at that particular positions. Okay, so the boundary condition has to be satisfied. That means it has to be 0 at the initial point and at all the boundary conditions. For hydrogen atom problem, your boundary conditions are like, for there the wave function is a function of radius, and it is equals to 0 at r is equals to 0 and r is equals to infinite. That means at 0 radii and at infinite radii, your overall wave function becomes 0. So these were your certain types of wave functions which are acceptable and which are considered to be acceptable in your quantum mechanics, and we have understood that why actually happens. Now we'll try to take a question which was actually asked in your GATE 2015 exam, and we'll try to understand that how to solve that question. Alright, so this was the question which was asked in GATE 2015 exam, and the question was like, which one of the following plots represent the acceptable wave function, the one which we have studied just now. So this says that which of the option is correct and why it is. Okay, so we'll also try to understand that why it is. Now you can look upon the options and you can easily see that option number A is not acceptable. Why? Because it's a discontinuous wave function, right? So it's not a continuous wave function, that's why it is not acceptable. Talking about option number B, so that is also wrong. Why? Because this is multi-valued wave function, right? So this is a multi-valued wave function. Talking about option number C, so that is also wrong because the first derivative has two values over here, or you can say that the first derivative is discontinuous. So what you can say, the first derivative is discontinuous in this case, right? So that's why option number C is also wrong. Option D will be your correct option, and this will be the one which will be acceptable by all the means, because this is single valued, this is continuous, okay, this follows boundary condition, okay, boundary conditions are also followed, and the most important thing is that the first derivative is continuous. You can draw the tangents at any point and you will see there is just one value of that. So that's why this wave function is a acceptable wave function, and this is how this question has to be done. I'll give you one question to solve of your own. Okay, I'll just give you some examples. You have to tell me that whether they are acceptable wave functions or not. Alright guys, so these are certain questions which I am giving you from my side. So I have made A, B, C, D, E and F. These are different graphs. The blue color line are your wave functions. Okay, so you have to tell that which of these are acceptable wave function, and if they are not acceptable wave function, then why is it so. Okay, so this is try it yourself. Okay, so try it yourself and do let me know in the comment sections below that what will be the correct answer, or which wave function is acceptable and which is not, and what is the reason behind it. Okay, so if you will be able to do this, then that means that you have understood the concept, and yeah, that's what it means. So this particular topic was very important from your GATE, from IIT JAM, TIFR and CSIR-NET exam. So that's all for this particular video guys. Thank you so much for watching. I hope whatever I taught you in this particular video was much useful to you. You guys understood that why do we have these conditions on a particular wave function for quantum mechanics. If you have any doubt, you want to ask anything, you can ask that out in the comment section below. If you are new to this channel, do subscribe to the channel. If you like this video, give it a like. Do let me know what you want to study in the next videos. So that's all from my side, and thank you so much for watching, and I'll see you in the next video. Till then, have a great day.